Hi guys, so in this video I'm going to present to you the proof of the mean value theorem, both in its single variable and in its multivariable version. Um, I'm going to use the Rolle's theorem to first prove the mean value theorem in its in its single variable version, and then I'll use that version to prove the multivariable version of the mean value theorem. So let's quickly begin by going over what the mean value theorem states in its single variable version. It says let a be less than b and let f be a function defined on at least the closed interval a comma b, and if f is continuous on the closed interval a comma b and differentiable on the open interval a comma b, then the mean value theorem allows us to conclude that there exists a c on the open interval a comma b such that the derivative of f evaluated at c is equal to f of b minus f of a divided by b minus a. So that is the mean value theorem in its single variable version, and that is what we are going to prove first. So let's just quickly begin with the proof. So we'll begin by setting up all the variables, and there will be I will have to use a little bit of geometry over here in order to make sense of why we are doing certain things in certain ways. So first of all, let's just set up the proof. Let a be less than b, let a be less than b, let f be a function defined on at least the closed interval a comma b. Assume f is continuous, on the closed interval a comma b and differentiable on the open interval a comma b. Okay, so we've set up the proof, and now I'm going to show you exactly what we are going to do. The idea is to define a new function that is somehow related to f, that will on which we will be able to use the Rolle's theorem. Now exactly how that function is set up is what I'm going to show you using a little bit of geometry. I can just go ahead and write out what that function is, and if you just use that function directly, you will get the correct answer, and I mean the proof would be correct. But if you don't know where that function is coming from, it seems like it would just be a weird proof if you don't know why you're doing certain things in certain ways. Okay, so let me just quickly show you exactly how we are going to define that new function. So let's assume that I have a function f that looks something like this. It doesn't have to, but let's just say it looks like this. Okay, and essentially the idea of the proof, or what the mean value theorem states, is that the secant line, the slope of the secant line that joins these 2 points, let's say that slope is m. Let's say that this slope is m. And what the mean value theorem states is that there exists a point on this graph such that the derivative of f evaluated at that point is equal to m. And that is basically what we need to show. Now, in order to do that, we are going to define a height function, which is going to measure the height, or the difference in heights between the function f of x and the secant line. Now, the way we do that is, let's just say that this point right here, that this point is x naught, right? So this is any arbitrary point x naught that lies between the points a and b. That's the only condition on x naught. Well, clearly the value of or the height of f at x naught is just f of x naught. And if I want to measure the height of this secant line at the point x naught, what I need is essentially an equation for the secant line. And I can do that quite simply by computing the equation of this tangent, the equation of the secant line. So I know that there are 2 points that lie on the secant line. Let me just take one of them, a comma f of a, and let me call the slope of this line m. Then I know that the equation of this secant line is simply y minus f of a, this is equal to m times x minus a. Or in other words, if I simplify this, I'm going to get y is equal to m times x minus a plus f of a. So this is the equation of the secant line. And if I want to measure the height of the secant line at x naught, all I need to do is replace this x with x naught. So in other words, this height function h of x, h at x naught in this case, is simply the difference between the height of the function f at x naught and the height of the secant line at the point x naught. Now, given this, let's just define this function. What I'm going to say is I define a new function, h, which maps from the closed interval a comma b to the real number system, such that h at x is equal to f at x negative m times x minus a negative f of a. So just to emphasize upon why this is a why this is the function we need, it is because of two things. Firstly, notice that if I actually compute the derivative of this function and I set it equal to 0, what I'm going to get is f prime of x minus m is equal to 0, and I will get an expression for f prime of x that is equal to m. And m in this case is the slope of the secant line, and the slope of the secant line is simply f of b minus f of a divided by b minus a, which is precisely what we want to show. We want to show that there exists a point C on the open interval a comma b where the derivative of f evaluated at C is equal to the slope of the secant line that connects the point a comma f of a and b comma f of a. So that's the first thing. The other thing you need to notice is that this height function, I mean, you can just see this from the geometry that we did. It is equal to 0 at both a, when evaluated at a, and when evaluated at b. You can also check that directly by substituting x equals a and x equals b in here. X equals a is pretty clear. If you just sub in x equals a, this cancels out and you get f of a minus f of a, which is just 0. In order to confirm, if what happens if you substitute in b, you need an expression for m, and I'll do that in a minute. So here's what I'm going to do now. Now I'll apply the Rolle's theorem, on h on the closed interval a comma b. Note, as f is continuous on the closed interval a comma b, so is h. This just follows because of the fact that m times x minus a is continuous everywhere. So the continuity and the differentiability of h both depend on f and not on this other part, because that is just continuous and differentiable everywhere. Okay, so we know that as f is continuous on the closed interval a comma b, so is h, and as f is differentiable on the open interval a comma b, so is h. Also, h of a is equal to f of a minus m times a minus a minus f of a, which is equal to 0, and h of b is equal to f of b minus, now the expression for m, I'm just going to substitute that in, that is f of b minus f of a divided by b minus a. I'm going to get b minus a minus f of b, minus f of a, and you can verify that this is indeed equal to 0. Thus, by the Rolle's theorem, we know that there exists a point C on the open interval a comma b such that h prime at C is equal to 0, which implies if you compute the derivative of h at C directly, you are going to get f prime at c from this expression. I'm using this expression. Negative, the derivative of this remaining piece is just m, it's always m, and this is equal to 0, which implies that f prime of c is equal to m, which implies that f prime at c is equal to f of p minus f of a divided by b minus a as needed. So this right here is the proof of the mean value theorem when it's applied, in its single variable version. And I mean, it's not a proof that it's like quite. I mean, once you know the proof, it is quite straightforward. But at first, when you're trying to prove this from scratch, it might not be as intuitive to define this new function h and then define it in this way. There are other ways to prove this mean value theorem that I've seen, one of which involves rotating the graph itself, because what ends up happening is if you define a new coordinate system where this secant line is actually horizontal, so you apply a linear transformation such that you get, if you apply a linear transformation to this function such that you get a horizontal line, and then you can directly apply Rolle's theorem on that. That is actually quite similar to what we've done here, but I mean, the actual write-up of the proof will be a little bit different. So that's another way you can prove this theorem though. Okay, so with that done, this is the proof of the mean value theorem when it's in its single variable version. Let me just label this once again, f for x naught, and this is x naught, and this is h of x naught. Okay, so now what we need to do is we need to prove the mean value theorem in its multivariable version, and the process is going to be the same. When we were proving mean value theorem in its single variable version, we reduced it to the Rolle's theorem. Now when we're proving the mean value theorem in its multivariable version, we are going to reduce it to the mean value theorem in its single variable version. But first of all, let's just go ahead and read what the theorem says. It says that f be a real valued differentiable function defined on an open set S, which is a subset of R to the power of n. Let A and B be elements in S, and let L with a subscript a comma b denote a line segment which joins the points A and B. And if this line segment is contained in S, then there exists a C on this line such that f evaluated at vector B or point B minus f evaluated at A is equal to the gradient of f evaluated at C dot product with B minus A. So that is what the mean value theorem states when it's in its multivariable version. There is one thing that I would like to emphasize over here is that f is a real valued function. In other words, f can map from any arbitrary set of R to the power of n, but it must map to the real number system. That is a condition which you should immediately see because of this equality. Clearly, the dot product of two vectors, it's always a real number. So this left-hand side should also be real. Now, there is, as I said, I probably mentioned this in the previous video, there is a generalization of the mean value theorem that applies to any function f, as long, I mean, not any function f, it has to satisfy certain constraints, but you lift the constraint that f is a real valued function. So there is a generalization that holds in this case. For example, f, it maps from R to the power of n to R to the power of m, for example. And there is a generalization that works in this case, as well. However, I'm not going to deal with that generalization in here. I will prove that when I'm proving the inverse and the implicit function theorem, because I'll be using the generalization to write out that proof. Okay, so let's just go ahead and begin with the proof of the mean value theorem in its multivariable version. I'm not going to set up, or okay, maybe you know what, I should just set it up again. So what I'm going to say is this is the second proof now. This is another proof. So I'm going to say let f be a real valued function oh sorry, real valued differentiable function. It must also be differentiable. Real valued differentiable function, differentiable function defined on an open set S, which is a subset of R to the power of n. There are two other assumptions we need to, or not assumptions, there are some other things we need to define. We say let A and B be elements of S, and let L, A comma B denote the line segment, the line segment which joins vectors A and B, or points A and B. Okay, now I'm going to assume that the line A comma B is a subset of S. So now what I'm going to do is I'm going to define a new function, and this is essentially the idea behind the proof. And the idea is to define this function f of, let's just call it gamma at t, where gamma of t is the parameterization of the line L, of this line segment that connects the points A and B. Now, the idea behind defining this new function is that it restricts f to this line, to this line segment, and more importantly, it gives us a function of one variable. Now, what we will do after this is, once we've defined this function appropriately, we are going to apply the mean value theorem in its single variable version, or the single variable version of the mean value theorem on this function, and that will give us the that will give us our conclusion. So what I'm going to say is, let gamma, which maps from 0 comma 1 to the line, to this line segment, be defined as phi of t is equal to t times the vector b plus 1 minus t times the vector a. And you can confirm indeed that this is a parameterization of the line L. Next, I define phi, which maps from 0 comma 1 to the real number system, as phi of t is equal to f at gamma t. Finally, I'll apply the mean value theorem, single variable, of course, or I should say the single variable version, the single variable version of the mean value theorem on phi, on the closed interval on the closed interval 0 comma 1. My bad. Okay. So what I'm going to do is I'm going to skip some of the verifications part, which you can do on your own. What I mean by the verifications part is the fact that phi is indeed differentiable on the open interval a comma 1, and it's continuous on the closed interval 0 comma 1. They basically follow from the fact that f is continuous on the range of phi, and the range of phi is the line segment that connects the points A and B, and the parameterization that maps to that line is defined on the closed interval 0 comma 1. So it's both continuous and it's differentiable it's both continuous and differentiable. The parameterization is both continuous and differentiable. It's continuous on the closed interval 0 comma 1 and differentiable on the open interval 0 comma 1. F is differentiable everywhere. In particular, it's differentiable on the line segment that connects the points A and B. That is sufficient to conclude that phi is differentiable on the open interval 0 comma 1, and since f is differentiable everywhere, it follows that f must also be continuous everywhere. In particular, it must also be continuous on the line segment that connects the points A and B, and that is sufficient to conclude that phi is also continuous on the closed interval 0 comma 1. So I'm just going to state that, but if you want to verify that rigorously, you can do that on your own. It's pretty simple to do that. Note, phi is continuous on the closed interval 0 comma 1 and differentiable on the open interval 0 comma 1. Then it follows that there exists a C on the open interval 0 comma 1 such that the derivative of phi evaluated at C is equal to, by the chain rule, it's equal to sorry, not the chain rule yet. So right now this is the mean value theorem. So it's f at gamma at 1 minus f at gamma at 0 divided by 1 minus 0. Okay. And now when you're computing phi prime of C, you can do that directly by using the chain rule. So this is equal to, by the chain rule, this is equal to the gradient of f evaluated at, you know what, let me just rename this S. It will be much, it will be just clearer, although you don't need to. So we're going to get the gradient of f evaluated at gamma of S dotted with gamma prime at S. And this is equal to gamma at 1, you can verify that is basically just the vector b, and gamma at 0 is the vector a. So I'm going to get f of b minus f of a on this side. Now, if you look at what this gamma prime at c is, this is basically just the slope of that line segment from a to b. Now, if you compute the derivative of gamma at s, here's how we had defined gamma. This is how we define gamma. You can clearly see that the derivative of gamma is basically just b minus a. And at s, doesn't matter what the point is, it's always going to be b minus a. So we don't need to worry about that. This is just going to become b minus a, and that is precisely what we want. So we have the gradient of f evaluated at gamma of s dotted with b minus a. Sorry, this implies, and this is equal to f at b minus f at a. Finally, observe that as gamma of s is equal to, or is an element, or lies on the line segment that joins A and B, we could say C, let C be equal to gamma of S, which of course lies on the line segment that joins A and B, and let's just call this 1. Then by 1, the gradient of f evaluated at C is a vector, so evaluated at C dotted with vector b minus vector a is equal to f evaluated at vector b minus f evaluated at a. And that completes the proof. That is what we wanted to show. We wanted to show that there exists a point C on the line that joins the points A and B, such that the gradient of f evaluated at that point dotted with b minus a is equal to f of b minus f of a. So yep, that completes the proof of the mean value theorem in its multivariable version. These proofs are not necessarily hard, but I've always enjoyed this exercise, especially because of the fact, I mean, if you think about how we proved this, we essentially began with the Rolle's theorem, which we had to prove on its own. Now, when we were doing the proof of the mean value theorem, or the single variable version of the mean value theorem, we reduced it to the role theorem. And then when we were proving the multivariable version of the mean value theorem, we reduced it to its single variable version and then computed it. This is, just a strategy that you often apply. You have a rather complicated theorem to prove, or a rather complicated question to solve, and you reduce it to an easier version and then solve it that way. So it's an exercise that I've always enjoyed. So yeah, that is pretty much it for this video. In the upcoming videos, I'll be presenting a couple of interesting questions, and then I'll be presenting the proof of the implicit and the inverse function theorem. And while I'm doing that, I'll also be showing you a more generalized, it's not really a generalized version, but what you can do with that version of the mean value theorem is that you can lift the restriction on f, which requires it to be a real valued function. So you can consider functions that map from r to the power of n to, say, r to the power of m. There is a more general version over there. These versions do not apply if f is not a real valued function. So that is a theorem that I will have to use when I'm proving the inverse and the implicit function theorem. So I'll prove that then. And yep, that is pretty much it for this video. I hope you enjoyed it. I'll see you in the next video.